I'm going to talk about spheres. I will assume that you're familiar with the notions of area and volume. If you're not, I would invite you to watch the necessary videos. All right? Now let me state what spheres are. Spheres are three-dimensional figures that are the sets of points equidistant from center points. All right, so for example, if I specified some point in space, such as that blue dot, and then I specified another set of points that were all a certain distance from that blue dot, okay, that other set of points would look something like the picture I just drew, okay? Now, that picture is denoting a three-dimensional figure, okay? The distance from the center to any point on the surface of a sphere is referred to as the radius, okay? And the center is the center point, okay? Now, I'd like to state the most important formulas to remember for spheres, okay? If we denote the radius by the variable r, all right, if we do that, then the volume of a sphere of radius r is 4/3 pi r cubed. Okay, very important formula. Now, what about the area of the the surface of a sphere? Okay, the surface area of a sphere is given by the formula 4 pi r squared. Now, there might be some people that are concerned that they'll get these mixed up, and they'll use the volume formula accidentally for surface area and vice versa. Here is one way to prevent that from happening. So the units of surface area are the square of some length unit, such as square centimeters. Okay. Notice that the surface area formula is squaring the radius. So that's going to have the right units for surface area, right? Furthermore, volume, the units of volume are the cube of some length unit, such as meters cubed. Notice that the volume formula is cubing the radius. So that's going to have the correct units for volume. That's one way that you can make sure to use the right formula. Okay, now I'd like to outline how you can derive these two formulas. Now, the derivation I'm about to show you is not so important as memorizing these two equations. Okay? Nevertheless, I'll go through it. Suppose you wanted to find the volume of a sphere of radius r, as I've drawn in my picture. Okay? So one way to arrive at the volume formula is to approximate half of the sphere by a stack of cylinders, all with the same height. So there I have a stack of 3 cylinders. The cylinder above the one below it has a smaller radius. Okay. Now, as I add more and more cylinders, I will I will approximate the volume of half of the sphere better. Okay. Now, suppose that I had n cylinders. So the full stack is the height of the full stack is approximately the radius of the cylinder. So the height of the cylinders, each of them, is going to be approximately the height of the full stack, which is approximately r, divided by the number of cylinders. Okay? Now, you can find the radius of each cylinder by using the Pythagorean theorem. Okay, so that green triangle will give the radius of the third cylinder. Okay, the hypotenuse of that green triangle is r. The short leg of that green triangle is the approximately the radius of that third cylinder. Okay, I will leave it to you to derive that the radius of the kth cylinder is approximately r times the square root of 1 minus k squared over n squared. Okay. Also, the volume of the kth cylinder is approximately pi r cubed over n times 1 minus k squared over n squared. Now, to arrive at those two formulas, you need to use the Pythagorean theorem, as I've stated, and also the volume formula for a cylinder. Okay? So the volume of half of the sphere is approximately the sum of all of the volumes of all of the cylinders. Okay? And the k runs from 1 to n, because we said there was n cylinders. Okay? Now, I will leave it to you to show that that sum is equal to pi r cubed minus pi r cubed times the sum for k going from 1 to n of k squared over n cubed. Okay? Now, as n gets larger and larger, okay, imagine taking n to be 100 or 1,000 or even 1,000,000. Okay, as n gets larger and larger, this sum will get closer and closer to the volume of half of the sphere. Okay. Furthermore, the sum there on the right of k squared over n cubed, that will get closer and closer to 1/3. Okay, I'll leave it to you to see why that is the case. Okay, so the formula there, we've got pi r cubed minus 1/3 of pi r cubed. Okay, so 1 minus 1/3 is 2/3, so that's 2/3 pi r cubed. And then that's for half of the sphere, so if we double that, we arrive at the final volume formula, 4/3 pi r cubed. Okay, I know that I just outlined a few of the steps, and again, this is not the most important thing to remember. The most important thing is to memorize the final formula. Okay, nevertheless, if you're interested, I would encourage you to try to fill in the details. Okay? Now, let me briefly outline how you would arrive at the surface area formula. Okay? Suppose we wanted to find the surface area of a sphere of radius r, such as in the picture that I'm drawing right now. Okay, so suppose we approximated the volume of that sphere by lots of thin square pyramids. Okay, so there's a thin square pyramid, and then I could put another one over here. Okay, it's like they're almost like little toothpicks. Okay, and so imagine that I just covered almost the entire volume of the sphere with these little pyramids. Okay, now every square pyramid is going to have some tiny base area. Let's call it A. Okay, and let's assume that I had n pyramids. Okay, the volume of any of the pyramids using the volume formula for a pyramid is 1/3 times the area of the base, we'll call it A, times the height, which is approximately r. Okay, now that approximation will get better and better as n gets larger and larger. Okay, so our volume approximation is going to be the sum of all of those pyramid areas. So 1/3 AR plus 1/3 AR plus 1/3 AR. And remember, we have n pyramids. Okay? So that's going to equal 1/3 times r, factoring that out, times NA. Okay? Now, as n gets bigger and bigger, again, imagine if n was 100 or 1,000 or even 1,000,000, then this approximation is going to get closer and closer to the volume of the sphere, which we've just established is 4/3 pi r cubed. Okay? Now, let me isolate n times a. So I can do some cancellation. All right, so I have that NA is equal to 4 pi r squared, and again, that's an approximation as long as n is some finite number. But as n, if we could take n equal to infinity, then that would be the exact value of NA. Okay, 4 pi r squared. So that establishes that the surface area of a sphere is 4 pi r squared. All right. Now I would like to do some examples using these formulas. All right. Let's find the volume and surface area of a sphere with a radius of 2 feet. So first the volume, 4/3 pi times 2 cubed. So that gives 32 pi over 3 cubic feet. Okay, and then for the surface area, 4 pi times 2 squared, that gives 16 pi square feet. All right. Now, I would like you to try an example. Would you please try to calculate the volume and surface area of a sphere with a radius of 4 centimeters? So pause the video and do that now if you like. Okay, so I'll go ahead and work it out as well. So the volume, 4/3 pi times 4 cubed, that gives, let's see, if I have to find 4 to the 4th power, that's 16 times 16, which is 256, times pi over 3 cubic centimeters. There's the volume. Surface area, 4 pi times 4 squared. 4 times 4 times 4, 16 times 4, 8 times 8, that gives 64 pi centimeters squared for the surface area. Okay? Now I'd like you to try a slightly different type of problem. Suppose I told you what the volume of the sphere was. Let's say the volume of a sphere was 5,000 cubic centimeters. Could you tell me what the radius was? Okay? So pause the video and do that now if you like. All right, so I'll go ahead and work it out as well. So the volume is equal to 4/3 pi r cubed, so I can isolate r. Let me multiply both sides by 3. Now let me divide both sides by 4 pi. Now let me take the cube root of both sides. Now let me substitute 5,000 for v. So 3v is 3 times 5,000, which is 15,000. Divided by 4 pi. 15,000 divided by 4, we can do that. That is, let's see, 4 goes into 15 3 times, with the remainder of 3. 4 goes into 37 times with the remainder of 2. 4 goes into 250 times, so 3,750 divided by pi centimeters. So that is the radius, and you can get a decimal approximation to that if you like. All right. Now, I'd like to close with one last type of problem. All right, try this one. Suppose a cone has a radius r and a height r. Suppose a sphere has a radius r as well. Find the ratio of the volumes of the sphere and the cone. So pause the video and work that out now, if you like. All right, so I'll go ahead and work it out as well. First, I'll draw a picture. All right, so the sphere has a radius r, the cone has a height r, and the cone has a radius r as well. Okay, and we want to find the ratio of the volumes of the sphere and the cone. So the volume of the sphere is 4/3 pi r cubed. We'll divide that by the volume of the cone, which is 1/3 pi r squared times r, since r is the height. And now we can do some cancellation. The pi's go away, the denominators go away, even the r's go away. So for this special situation, the ratio of the volumes is 4. The sphere will have 4 times the volume of the cone.